All right, let's resume. So this morning we discussed the remainder of the slides on OpenMP 3.1, and we also talked about Intel Inspector and some other tools which can help you use detect race conditions and so on. Are there any questions about the material we covered up to now? Feel free to put them in the chat if any. If not, let's continue and talk a little bit about what was added to OpenMP in versions 4, 4.5, and a little bit in version 5. So this is a bit of an overview of what we're going to talk about with respect to extensions in OpenMP 4. So basically, we'll talk about thread affinity, and that is indeed already touched upon. With respect to performance, this is quite important because if threads can just wander around, we're going to be unhappy performance-wise. And then there is also a completely new concept in OpenMP, and that is SIMD, so single instruction multiple data, and that is used to vectorize both zero and parallelized loops. So we'll see how to use that as well. Then there is some support in 4 about support for accelerators. So basically to device construct and data movement, but in OpenMP 4 that was really rudimentary. So more has been added in 4.5 and in 5. Tasking extensions. So basically, one of the things that was added was a depend clause and task group construct. And then you can do user-defined reductions. Some enhancements to atomics, and then cancel and cancellation points, again for tasks. And OMP display environment, which is nice. It allows to run the program, but to display all settings. So that is that can be convenient for not so much for debugging, but essentially for verifying that your assumptions about your environment are correct. Okay, so the very important thing is indeed MP places and thread affinity, and that basically determines where threads will be placed. And those can be controlled in a few ways, but you can do that, for instance, using environment variables. And the environment variable of interest here is OMP places. And that can be done at a logical level or at a physical level. And for that, we need the notion of a place. And a place can be a couple of things. For instance, a place can be threads. So basically, each place corresponds to a single processor, or in other words, the hardware that handles a single thread. So that is very often not relevant in the context of HPC, but on my system it would be relevant. Let me show you what I mean. So basically, I'm just going to show you on Windows, but it's the same on Linux, of course, because this is a hardware thing, not a software thing. So essentially, if you look at the CPU data here, come on. Yeah, the CPU data here, you will see two things. You will see the number of cores, and you see the number of logical processors. And the number of logical processors is double that of the cores. So basically that means that each core can actually handle two threads sort of independently. Now the emphasis here is on sort of, and that depends on the hardware. What was a problem back with earlier processor versions? So for the latest Intel processors, this is, as far as I know, no longer true. But for earlier versions of Intel processors and for AMD, it's indeed true that much of the logic of 2 threads can be handled by a single core, except that the logic to handle floating point operations is not doubled. So that means that if the 2 threads both need to do floating point computations, they'll actually be serialized, because the computations, the first thread needs to do the computations, the second thread needs to do the computations. So basically, this is going to result in a lot of thread suspending, resuming, while the other thread is actually using the floating point unit. So hyperthreading, as this is often called, is quite useful for a desktop system or for a laptop. It's also quite useful for applications such as web service or other, other server-based operations. But in scientific computing, it's not necessarily something useful. On the contrary, it may actually slow down your execution. So, but it's possible. OpenMP supports to actually use to pin at the thread level. So that is possible if you use OMP places as threads. So in HPC context, OMP places cores is more useful. Then that means that each place corresponds to a hardware core, essentially. So it is a single core, not the two not hyperthreading, but if hyperthreading is switched off. And you can also specify sockets, and then basically that means that each place corresponds to the processors of a single socket. Okay, so basically all the threads, all the hyperthreads, and so on. Okay, so essentially those are abstract names, but you can make that also numerical places. So that's also possible. But in general, numerical places are hardware dependent, in the sense that the semantics of that may differ between AMD CPUs and Intel CPUs. So it's a little bit tricky to be sure that the right thing happens. What do I mean by that? So basically, the explicit numbering thing here is mentioned. So we've got 8 places, and each place consists of 4 processes. So each pair of curly brackets is essentially a place, and in those the numbers denote the processes. So now it depends, and that's the problem, it depends on how the places are numbered. Because on some hardware, 0, 1, 2, etc. will refer to the first hyperthread, let's say, on each core. And then the higher numbers will refer to the second hyperthread. On other hardware, it's just that 0 and 1 will refer to hyperthread 0 and hyperthread 1 on core 1. 2 and 3 will refer to the hyperthreads on the second core, and so on. So if you know how your cores are numbered, it's not a problem. But the problem is that it might be different on different systems. So basically, that's not necessarily the best idea. And as you can see, there are different ways to formulate this. So you can be very explicit and enumerate the whole lot, or you can use a different notation where you give the starting ID and the number you want. So basically 0:4 would mean 0, 1, 2, and 3. 4:4 would mean 4, 5, 6, and 7, and so on. Or you can say, alternatively, I've got 0 to 4, I have 8 places, and I increment by 4 each time. So that's yet another notation to do the exact same thing. But in general, I would suggest that you use abstract names rather than numbers. Okay, so process binding. So we have our places. So in this particular case, if, for instance, we would have, let's say, a system with 32 cores, then this would basically mean that we have 32 places, each bound to a specific processor. Okay, and that would be the same as threads in this case. Okay, so we now export the number of threads as 4, 2, and 2. So basically that has to do with the different level of parallelization. So essentially what we will get with OMP proc bound, we'll do spread, spread, and close. Okay, so this is for multi-level parallelism. So that means we have a parallel region within a parallel region within a parallel region. So at the top level, we will actually have 8 threads. Okay, and the proc bind is set to spread. That means they are as far apart as possible. So if we have these 32 places, then those upper level, the first pragma here, threads will be put as far apart as possible. So basically that means with a spacing of 4. So these are the guys which are spawned in this outer parallel region. So the second parallel region will only spawn two threads for each of those 8, obviously. And again, we get a spread. So they will be as far apart as possible. So basically that means that the second level parallel region will spawn 2 threads. Well, one is the master thread, and so it will spawn a new one. So 2 threads in total. So at that level, at the second parallel region, we have 16 active threads. And they are spread, so basically they're being put with a distance of 2, in this case, half the distance of the place above them. Okay, then we have a third level of parallelism, so the third pragma. Again, we have 2 threads, but they're close. So basically, these 2 guys, this guy here, is going to generate this thread. This guy here is going to generate this thread. So basically now we have 32 threads, and they're at this level grouped into groups of 2. So that's basically what is happening here. Of course, this is only relevant when you have nested parallel regions. So basically, that is what happens here. Okay, so what can you have? You can have either spread, basically distribute sparsely. Then you have close, that basically new threads are as close as possible to their parents. Okay, so in the same place list, of course. And then master, all new threads are in the same place as the parent. So that's basically the idea here. So this allows you to control, also in a use case where you have multiple multiple levels of parallelism, where your threads are going to end up on the actual hardware. Okay, so why do you want to do that? Well, basically you want to ensure data locality. That's at the end of the day what you want to achieve. And so for instance, here we have the 4 sockets. So 4 socket systems in HPC are somewhat rare because the hardware is very expensive, and the only reason why you would want them is to make nodes that can really handle very large amounts of memory. So that's a use case for 4 sockets machines in HPC. But then again, Nowadays, it's actually cheaper to have 2 sockets machines and larger memory chips. That's actually cheaper to get to the same amount of memory. But yeah, it's possible, and here, by way of example, it's actually shown. So what do we have? We have 4 sockets. Each socket has 6 cores. Okay, to find a chip that has 6 cores, good luck with that, but okay. And then you have 2 hyperthreads per core. Okay, so in total, that gives us 48 processors. And then you get the vendor's numbering, so that depends, as I already mentioned. So in this case, and this is the numbering which we're going to assume, it's round robin over the sockets, okay, and then over the cores, and then over the hyperthreads. So basically, we've got 0 here. Round robin over the socket means that 1 goes to the next socket, 2 goes to the 3rd socket, and 3 goes to the 4th socket. Then we're again at the 1st socket, so that gets 4, 5, 6, 7, etc. So the upper row here, everything that's numbered from 0 up to 23, that is the first hyperthread, let's say, on a core. And then everything from 24 up to 47, that is the second hyperthread on that core. So basically that means the red rectangles here denote the 4 sockets. The light blue rectangles denote, okay, again, the socket. But basically the blue rectangles denote the core. And the 2 numbers are the 2 hyperthreads of that core. So the numbering, this is of course specific, as I mentioned, to the hardware vendor. So that's something that you're either aware of or don't use directly, one of the two. So basically, if we specify OMP places threads, then we would actually get something like this. So basically, the tasks are pinned to hardware hyperthreads. That's basically the idea here. Okay, we can also export OMP places, set it equal to cores, and then a place will actually be a core. So that means that 0 and 24 is going to be one place, 4 and 28, etc. We can also create a place per socket, and that means that we get everything, well, not everything, that we get 0, 4, 8, 12, 16, 20, 24, 28, 32, 36, 40, and 44 in one place. And then, of course, we have the next place for the next socket and so on. So basically, you should really use these because that is vendor independent. So if you don't have any nested parallel regions, then of course the number of threads is going to be the 4 times 6 in this case, and the proper bind is spread. So basically, you can do this also when you enter a parallel region. You can actually do binding. If you have nested regions, then of course the product here should be equal to the number of threads which you have. Okay. So here you would get 1 thread per core. Here you would get 1 thread per hyperthread, essentially. Okay. Is this more or less clear, the whole placement thing? So what you want to achieve is basically that your threads get bound or get pinned to certain places, that they get onto the hardware that you intended to. And of course, the main reason for that is cache reuse, because that will be optimized if you are sure where your threads are and take it into account when you're programming. Okay, so another new thing which is quite useful is vectorization, and that implied that we have a new construct, the SIMD construct. So what we can do is apply that to for loops, and in Fortran, of course, also to do loops, depending on which programming language you are doing. So, of course, for Fortran, we would have an open SIMD and an open and an OMP SIMD and OMP and SIMD. Okay, so essentially that means, of course, that just like for any type of parallelization, that the for loops, the iterations, should be independent so that they can be executed in parallel. That's basically the idea. So here's a more concrete example. We would have pragma OMP SIMD on a for loop. And that basically means that vector operations are applied over these arrays. So essentially it means, again, depending a little bit on your hardware, that for instance, 4 double precision values are being added simultaneously of B and C and stored into A. That's basically the idea. So why 4? So basically it depends on the size of your registers. And depending again on your hardware, you will certainly have 256-bit registers. Okay, so essentially double precision is 64-bit. So you can have 4 of those. So one register of with 256 can store 4 double precision values or 8 single precision values. Hence the 4 here if we're assuming double precision. So that's for all hardware. Intel hardware since Skylake actually can use wider vectors, wider registers with double the size, so 512 bits, which means that they can store 8 double precision values or 16 floating point values. So that means if you have an iteration such as is depicted here, so a for loop over a long array, and you do an operation like adding 2 arrays element-wise, actually in each clock cycle, 4 of these values in double precision will be added at once. So that means that suppose you have an array of length 10,000, okay, you only need 2,500 cycles to do the additions. So that's of course quite cool, and it's very important to try and make use of that because it's going to speed up your application potentially by a significant factor. Modern Intel hardware also has something which is called a fused multiply add, and that essentially means that if you have an operation of the type A is equal to B plus C times D, that operation is also going to be done on average in a single cycle. So I'm slightly lying here because it's not being done in one cycle, but on average it takes one cycle thanks to pipelining, but that would lead us a little bit too far. You can just think of it in terms of average. Okay, so there are 2 things here. Is that faster? No, it's doing something different. So essentially, the pragma OMP SIMD by itself is not going to parallelize things. It's just going to ensure that vectorization happens. That's all. So this code, as it stands here, is going to be run by a single thread. Of course, if you have a long loop, then of course you are going to use both SIMD and for, the two together, and then you get both. Each thread will do things vectorized, but you will have multiple threads. So they are kind of orthogonal to one another. You can combine them if that's useful. For instance, if you have a loop with 10 iterations or with 12 iterations, it really doesn't make any sense to use a for, an OMP4, because the overhead of creating, of managing the threads, the iterations over the threads, is just not going to outweigh the potential benefit you will have for doing so few iterations. But on the other hand, OMP SIMD might still make sense, because it might be that this can be vectorized. Well, you're actually saying that it can be vectorized. So that is when you would use, for instance, an OMP SIMD, but no OMP4. And of course, there are also for loops where vectorization doesn't make any sense. For instance, if you have something that works on objects, then, for instance, in C++, if you have an iterator, random access iterator, which you use an OMP4 on, then switching on vectorization doesn't really make any sense, because the operation on that object itself is probably not being subject to vectorization at all, unless it's something really, really simple. But otherwise, it's likely nothing is going to happen. So there it would not make sense to add a SIMD directive on top of a for directive. So they are really orthogonal. Does the compiler add vectorization when it is possible? Yes and no. So basically, in -02, the optimization level, it's not going to do that. So in that respect, the answer is no. If you ask the compiler to do it by switching to -03 and eventually also give specific instructions to vectorize, it will of course do that, if it can. And there's the catch. So you can see there are a lot of clauses which you can put on such a SIMD directive. And that's where the catch is. So the problem is with automatic vectorization done by the compiler, just by specifying the appropriate level of optimization, or choose your favorite by specifying flags that ask it to vectorize. The problem is that the compiler is only going to vectorize what it can mathematically prove to be safe. Okay, and the point is that certain things can be vectorized if you add a little more information. Then the compiler would be able to prove that it can be vectorized, and it's going to do it. But there is no standard way of adding that information in your programming language. So that is always something that is somehow compiler dependent. And each compiler actually has certain pragmas that are not OMP pragmas, but another type of pragmas that give you the possibility to add information. So for instance, the Intel compiler had a SIMD pragma, or has a SIMD pragma, outside of the scope of OpenMP. But the problem is that GCC doesn't understand this pragma. So basically, what the merit of the OpenMP SIMD thing is that it allows you to give more information to the compiler about your loop, so that it can actually vectorize things which otherwise it couldn't. And it can, that is compiler independent. So there's nothing compiler specific about it. This information is understood by all compilers regardless. So that's the big merit of this. And you can already guess that actually there are a few things which are additionally here, like safe len. That already tells you that there are operations that can be done provided you know something more about the structure of the loop. So you have the normal clauses here, which you would expect: the collapse, the reduction, private, and so on, last private, etc. So all these guys we know, there is nothing special about them. There are a few new ones: safe len, linear, and aligned. And those are specific for SIMD. So what does safe len mean? It actually means that in this case, if we look at the code, we actually have loops that seem not to be independent. And indeed, they are not independent. The loop for index I depends on the loop for I minus 100. So if your compiler looks at it, it will say, okay, I'm not really inclined to vectorize this because these loops are not independent. So I'm not going to do that. However, you can say, okay, compiler, I give you a SIMD pragma, and I'm saying that the safe length is actually 4. Basically, it means that if loops are 4 iterations apart, it's actually safe to, if indices are 4 apart, it's actually safe to vectorize. Because the A minus 100 or A minus whatever will already have happened if I is larger than 4. So that is the safe length. More or less clear? So basically, that's the delta L thing. So essentially, if the displacement is large enough, then it's safe to vectorize. And that's a guarantee that you can give using that safe len directive. Now, of course, it's you giving that guarantee. If your code violates that guarantee, the compiler is still happily going to vectorize your code, and your code will produce the wrong results. Because you said the safe len was 4, and you don't respect that by, for instance, having AI is AI minus 2, and then you have a problem. The compiler will vectorize. You said the safe length was 4, which is not true. Okay, so this is quite useful. You have to be a little bit careful here, because in OpenMP 5, this changed a bit. So the safe len is actually the actual length now. So yeah, it's the it's +1 essentially. So you have to be a bit careful with that. Okay, then the linear is also quite useful, and that basically is if you have a step operation here. So as you can see here, also something quite spooky happens from point of view of the compiler. So we have a certain step, which is a certain index, which is k, and we have a step, a step size for that expression. And as you can see, in each iteration, I'm changing k by the step size. So k is going to increase for each iteration of I. And that again is something that the compiler is going to say, well, okay, I'm never ever going to vectorize this unless you give some more information and give it some mathematical guarantees. So in this case, you would add to the SIMD instruction, the clause linear. You specify the value of the step, so that's the starting value, and you specify the step size. And then, of course, the compiler again has more information, and it knows that it can potentially vectorize this. So, of course, as the name implies, this will only work if that index is changing linearly. So if the step size remains constant throughout this do loop. So it should never change, and it should be specified in advance. Okay, this we know. That's all the same stuff. And then align. So basically that means that all the items that are listed will have a given alignment. And that, of course, is important with, for instance, malloc and so on. You can do that. You have to do that. You should really do that if you have an attribute align, for instance, in this case, on 64 byte boundaries. Remember the 64? That's the number of bytes of a cache line. And that's an attribute which you can give to a variable so that it actually gets in memory on a position that puts it at the start of a cache line. And that means that's a mechanism to ensure that you can to ensure that variables are never sharing the same cache line. Remember why that was necessary? We needed to ensure that if we wanted to avoid false sharing. And that's where this attribute thing comes in. So that's a C thing, of course. Here we would have a malloc that actually also aligns the data. So the array itself is guaranteed to start at the beginning of a cache line. And if we do that, then of course we should specify the variables that are in fact aligned, and we can specify the alignment of them. So this is also a quite useful one for certain optimizations. Okay, so we can have an OMP4 SIMD. So that's indeed combining both. Small question, yeah. Multi-level parallelization, okay. Is thread private shared then also specified per level? Yes. Yes, that would be the case. You can specify the privacy at each level, but remember, if you do that with just private, you will get new copies. If you have thread private, you still get new copies, but they will be initialized by the value it has in the context, where you do the second level parallel, the second parallel region, second level parallel region. Thread private. Yeah, so that would also be level by level, as far as I know. Yeah. Yeah. Sorry, I was thinking of first private first, but for thread private, yeah, I think it's also level by level. It should retain that value. Yeah, but level by level. Okay, so basically you can combine for and SIMD. So basically you can't do it in two steps essentially. So if you want to parallelize a for loop with both for and SIMD, you have to do that in one directive. That's basically the idea. But of course, you can have just a for or just a SIMD. Only you can't have both pragma OMP4 followed by pragma OMP SIMD. That would not make sense. So then you combine them. Of course, that is just essentially yeah, a sort of convenience. And then, of course, you can have pragma OMP parallel for SIMD, blah, blah, blah. But that is, of course, just a convenience. This is a necessity. Loop SIMD construct. This is just a convenience. Okay. All right, so basically that means the second bullet point here means if you have, for instance, a private that is going to apply to the do and the SIMD and not to the parallel. It doesn't matter much in this particular case because it's just do loops anyway. So typically, and the parallel region is going to close after the do loop. So yeah, well, that is a technical detail which normally doesn't matter that much. All right, so one of the things, of course, that makes your life a bit harder is when you have functions that are being called in for loops. Because how are you going to vectorize those? How is the compiler going to do that? Well, no, not how are you going to do it, how is the compiler going to do it? And actually, that's also a very nice thing. OpenMP actually allows you to create vectorized versions of your functions automatically. So basically, let's first look at our function. We get a number of arguments, x1, y1, x2, y2, and it's going to do this computation, which is sort of a distance between a point and another point, essentially. It's that. It's not really a distance because we don't do the square root, but whatever. Okay, so basically, I can add a pragma to that, which says that I declare this to be SIMD and that it's not going to use in a branch. Okay, so basically that means that there will be no if statements in the for loop where this is going to be used in. So it is going to generate additional vectorized versions for this particular routine, so that basically it can be applied vector size. So essentially, this says, okay, we're not going to ever call this in an if. So in a SIMD loop, this is guaranteed by this not in branch. Okay. So for example, here we have an OMP parallel for SIMD, and we are going to call our what's it called, square distance on basically 4 arrays, x1, y1, x2, y2, each time element I. So a special vectorized form of this function is being constructed here, being made available by the compiler and being used here during the linking process, so that this whole operation is going to be vectorized. Okay, so what I shouldn't do now, because that would not work, that is saying, okay, if I is even, then I'm going to do this operation. In my for loop, that would not be allowed because I've put here not in branch. So no is here. Okay. However, if you're sure that you are going to use it in a branch, or if you think you might use it in a branch, you can add the in branch. But of course, that means that lots of versions of this function are going to be generated with masking, and yeah, that blows up your code, it blows up complexity, so maybe that's not brilliant. And then you can also specify the SIMD length, so basically the vector length of the generated vector routine. And then of course it must be a constant expression, and you can have several of these with different clauses, different SIMD len clauses. Okay, and then again we have aligned to make sure that the compiler knows that what you're using is in fact going to be aligned at certain boundaries. Okay, and then uniform. Current locations. Yeah. Okay. So basically, if there are, so here, of course, all the arguments of my function are in fact vectorized. But suppose that that function would have an argument that is always the same for each iteration, then I can declare that with uniform with the name of this argument or these arguments. And then of course the compiler has more information and it can again do the smart thing. And then of course again, if necessary, we can put this linear clause if we have some index that happens to change linearly. Okay, so here we have in branch. So this function, this version of square distance actually can be called from within a branch. So here, for instance, we have a condition, an if and an else. And so basically, depending on on a certain condition, we either call we either assign to di or we assign to ei. Apart from that, the call is the same, but of course, given that for I and I plus 1, so this condition can have another value, it actually means that we have to have masked versions of these function here, so that the computations are done correctly. So this in branch means it's always going to be called from within a branch. So that means that you can actually have both versions. You can have a branch, an in branch and a not in branch version, and then the compiler will do the right thing in both circumstances. Okay. Okay. So certain optimizations may be a little bit problematic with respect to inlining. So yeah, a little bit of care is required, and the general advice essentially is try to avoid branches in for loops anyway, because that's going to be a problem for performance at some point. So okay. Of course, if you can rely on the vectorization of the compiler, yeah, then you don't have to worry. So use SIMD, OpenMP SIMD constructs when you know that the compiler is not going to do it because it can't prove, for instance, that certain conditions hold, which you can specify with the clauses on a SIMD directive. Okay, is this more or less clear? All right. Then array sections. So basically, you can work on array sections, but there are some restrictions. So basically, it can only in clauses when it's explicitly allowed. That's already very interesting. So you can use it in a map and in target constructs. Map and target is basically something that has to do with accelerators. So map is going to do a mapping between host and device memory, and also transfer. Well, okay, will cause transfer to happen upon entry and upon exit from target code. And OMP target, of course, is something that you want to happen on the accelerator. So yeah, that is something that, of course, we will touch upon, but not too much in detail. And then that also works with the depend clause on OMP tasks. Okay, GPU programming. So yeah, there is a little bit in OpenMP 4, and there is more in OpenMP 4.5 and even more in OpenMP 5 on GPUs. So we will discuss that a little bit, but not too much detail. I'll just give you the flavor of how it works without going too much into details. Okay, so that was the new stuff for OpenMP 4. Then OpenMP 4.5 added more stuff. So the main thing I think is a task loop, and also task loop SIMD. So that's a different way to deal with loops. Then more support for Fortran 2003. Oh, great. We're 2015 and we're getting complete support for Fortran 2003, while there's already Fortran 2008 and Fortran 2018 is on the horizon, since it was actually supposed to be Fortran 2015. Okay, remember what I said, that there was a lot of discussion required between the people who write the OpenMP specification and the Fortran/C++/C specifications. Okay, so this is one of the places where you actually see that pop up. One of the things, for instance, is how does your OpenMP, how is it going to interact with Fortran blocks? Interesting question. At the moment, the answer is that it depends on the compiler. So yeah, great. So that's what I mean with needing to talk about semantics of the language and specifications, etc., etc. Okay, then the linear clause can now also be used on ordinary do and for loops, which is also interesting because it also allows parallelization to happen safely. So that is interesting as well. And you have the SIMD length also for the SIMD construct. Then ordered can now have an argument, so the clause, and the ordered construct can also have that, and that basically gives is required for nested loops. So that is similar to what you could already do with collapse, for instance. The collapse would also have tell you that you could, or tell the compiler that it could merge the iteration space of nested loops. So here you now have the same for ordered. And then there's a priority clause for tasks. So you can actually specify a priority for tasks so that they get scheduled in a more intelligent way. And then there is a possible if clause on some combined construct. Okay. And a few things which we're not going to talk about anyway. So basically the SIMD construct, yeah, we already had that. So the new thing here is SIMD len. This we already had, so why is it here? We already had this, so I'm a little surprised here because that's the same as before, as far as I know. So, okay, yeah, so that's the point which makes it new. You can also do that now for loops. Okay, yeah, great. Then safe len we already had. I think. So that is also nothing new. The SIMD-len, that is new. So basically it specifies the preferred number of iterations to be executed concurrently. So that allows you to control whether you actually want to use, for instance, only the 256-bit part of the registers or the entire 512-bit registers. Okay, why? Well, there is a catch. So naively, you would say, well, okay, if I have 512-bit registers and I can do operations on 8 double precision floating points values at a time in an array, why would I not do that? I mean, potentially it could double the performance of my code. Yeah, sort of, except that the problem is that the energy consumption for 512-bit registers is significantly larger than if you just use the 256-bit registers. Okay, as such, who cares? Just pay a little more for electricity and you're done. Well, no. Problem is that that also increases power dissipation. And power dissipation means that you can't cool your chip enough. And that basically means that you have to drop the frequency at which the clock operates in order to compensate for that. Your chip will be running slower to compensate for the extra energy usage, which it can again reduce by reducing the clock frequency. And that is what's going to happen. So if you run code that is vectorized with SIMD instructions for 512-bit registers, you should realize that if you do that on all cores, that your frequency of your CPU is going to be reduced, and that hence things may, in practice, actually slow down rather than speed up by using those registers. And hence that's something that SIMD-len gives you control over by specifying, okay, I really want you here to use a SIMD-len of 4. If this is double precision, then basically that means that you will be using the 256-bit registers rather than the 512. You can also use it in the opposite way. If you really want to use the 512-bit registers, then you can specify 8 rather than 4. But of course, realize that that might give trouble with instructions that don't make any sense on older hardware. Okay. So yeah, it's what you want, not necessarily what is going to happen. And still, you need a safe LAN if required. Okay. Okay. And then the task loop. The idea is actually to do the iterations as tasks rather than rather than with a for construct. So the question is, why on earth would you want to do that? So there are a number of advantages. A few threads could be executed more or less computationally intensive things, while some others are in the loop are executing other tasks. So basically, the main point is nested parallelism. So essentially, that is something that you can easily get when you're thinking in terms of tasks, and which is much more difficult if you're thinking in terms of parallelized for loops and sections and such. Then that is a lot less convenient. So here's an example. We have a parallel region that has 2 threads. Okay, it also has 2 sections. So each section is actually going to be run by one thread. Okay, so basically, the first thread is going to run something that is not particularly computationally intensive, and then the other thread in the second section is going to open up another parallel region with 7 threads. So essentially, we will have 8 threads, 1 thread which is doing the first section, 7 threads which are doing the second parallel section. And so those are going to do these, in this case, 100,000 iterations. So to get this correct in the sense of to get load balancing as good as possible, it actually means quite a bit of experimenting. Because, okay, how much less intensive is section 1? Is it really 7 times slower than the other section? So to get this right is not so easy. And that's why it's much easier to do this using tasks, because then, of course, as soon as the task is done, the thread which is executing it can participate in some other task, can do some other task. So that gives you a lot more flexibility. And of course, if you know a little bit about how TBB works, that is exactly how TBB works. So basically for multi-level parallelism, tasks are really interesting. And that was, of course, why task loop is introduced. So basically, that is actually the advantage. Okay. So obviously, what you have to be aware of is that a task loop essentially has the same advantages or disadvantages, depending on your point of view, of a dynamic schedule, because a task loop is always going to be dynamic. So in all cases where we said, okay, dynamic schedules, guided schedules, be careful with respect to this and this and this, the same applies to task loops. So it's not as if task loops is going to solve everything. On the contrary, it certainly has issues, but to deal with especially nested parallelism is actually a rather interesting approach. So basically, that's why it was introduced. Okay, so we just retake a few things here. Probably not really necessary, but okay. So basically, remember, this was the traversal of a tree, and we use tasks. So the processing of the left subtree and the right subtree was done within a task. Okay. Then in our main program, we had a parallel region. So basically, we get a team of threads, and then one thread is going to start the traversal of the tree at the root. And then, of course, we get more and more tasks here, spawned each time that each task spawns new tasks, 2 new tasks essentially, up to the end where there is no left child or no right child or no child at all. Okay, so yeah, we did this basically. That was dealt with yesterday. So there's nothing new here essentially. Okay, so same thing for Fortran. All right. Then the task directive. Remember, we had a couple of clauses: untied, default. We know what this is. Private, first private, shared, and an if clause. So again, nothing new here. Some comments about the tasks. We mentioned that earlier. This is really a retake of what we had yesterday. So the takeaway point is a task can be executed immediately, but can also be deferred. And then that means that the remainder of that code block is being executed rather than the task up to potentially a task wait. The if construct helps to avoid tasking when there would be too little to do. So if you can quantify that in some way, and then this if clause is quite useful. For instance, to give you an example to make this concrete, one thing you would do with this is parallelize quicksort. And essentially, if you parallelize quicksort, you sort smaller and smaller lists. So you can do that by tasking. You sort a whole list by sorting 2 sublists, okay? And you do that recursively. So of course, if the list to sort is getting too short, then of course it doesn't make sense to keep on spawning new tasks. So then you just do it serially. And that means if you have an if that involves the length of the list to process, if the length is too small, then the task is not spawned and the current thread is going to execute that code itself. Okay, task scheduling points. So basically when a task is generated, and in a task that is generated, when the last instruction of that task is done, untied tasks wherever, essentially, and then at explicit and implicit barriers, and in task wait. So those are your scheduling points. Task wait, rather straightforward, nothing special here. That would be the task wait in Fortran and in C++, LU decomposition, blah. Okay, the single directive, we also remember, it's just the first member of the team that arrives there, goes into the block, executes the code, all the rest waits at the end of the construct and doesn't do anything which is in the single construct. Okay, that we know. And then the task thing, the sections thing, I don't think we need to repeat that. It's very straightforward. Okay, do 4 directives, we know that. Okay, now the syntax of this, we've seen that quite a bit. Okay, so now the task loop. So now things get more interesting again. So we have a task loop directive, and you can sort of view that as a do or for in Fortran, except that the mechanism by which the iterations are done is different. That's basically the idea. So the same caveats apply. So for a for loop in C and C++, it must have canonical form. Remember, we had to initialize our loop variable. The condition loop variable had to be simple, just a comparison with a comparator operator. And the update of our iteration variable had to be constant. So we couldn't fiddle, and we shouldn't fiddle with the boundaries of our loop. So the maximum value should remain constant throughout the loop. It should be an invariant. So those were the conditions. Or alternatively, only in C++, it should be an iterator with random access. Okay. So the same applies to task loops. What clauses do we have? We have an if. So that's nice. If we have too little to do, we can actually just decide not to do that. Shared private, no surprises. First private, no surprises. Last private, no surprises. Default, no surprises. Collapse, again, if you have multiple lists, you can merge the iteration space into one. And then we have the grain size. So you can either specify the grain size or the number of tasks, and those are mutually inclusive. So essentially you can say, okay, I want to have at most that many tasks, and then the grain size is determined from that. Or you say the grain size is 500, and then of course that determines the number of tasks. It's one of the two. You can't have both, which is fairly obvious. Then you can also specify that the task loop is untied. which has to do with the scattering points, remember, and mergeable, which we will come back to. There is also final. So if that's true, then all children tasks generated from these tasks will be sequential. So basically, if in our task loop there would be code that would generate new tasks, and final is true, that's not going to happen. It's basically like having an if clause on those tasks in our loop, and then all setting them to false. So that's what final is actually doing. And then, of course, we can also set a priority. Okay. Then, since OpenMP 5, you can actually also do a reduction on task loops, which was not possible before. Okay. There are a few clauses that are not applicable to task loops, and that's schedule. Yeah, of course, it doesn't make any sense, because you think of tasks of independent things to do, so how would you schedule them with static or with whatever? Doesn't make sense, so does not exist. And also linear does not make much sense, since essentially, yeah, what is going to be linear here? Everything is an independent task. All the iterations are divided among tasks, either by the number of tasks you set or the grain size. So how would that be linear? And the same applies to ordered. Okay. So first touch again. If you have task loops, of course, this also gets interesting, because then, of course, in a task loop, that again doesn't make much sense. Okay, we know that. Now, if we're going to have a task loop here, this is just a repeat of the same slide, actually. Yeah. Okay, probably as a reminder that in fact, if you have a task loop, you're going to have this problem anyway. Okay, yeah, so basically that's indeed the point, which you have to keep in mind. Okay, then single and task loop directives. So essentially, we would have to enclose the task loop thing in a single directive, because otherwise what would happen is that without a single directive, each thread would in fact do this loop, and that's not what we want. We want a single thread to create a task loop, so to spawn, in this case, 4 tasks, which are, well, a number of tasks, actually more than 4, which are going to be executed by several threads. So it's not a problem to create many more tasks than there are threads in order to get good load balancing. So that's not an issue. It's more or less the same what you would have if you compare a static schedule, standard static schedule, with a dynamic schedule for loops. Okay. This is the same thing, but then in Fortran. So don't forget the single, because otherwise you will have interesting problems. So sections and task loop. So basically here we have a Pragma OMP sections, and then in each we have a task loop here, and we have a task loop here. So basically this is section 1, and that is doing an MPI communication somehow, and it's going to do some numerical computations that use the Halo data. So that's going to happen in this section, and the other section is going to do all the computations that have nothing to do with the Halo data. So basically, as you can see, they sort of do the same thing, except of course that the number of iterations, since we're here operating on our complete domain, is much larger. And of course that in the first task, we first have to do the MPI communication, and only then can do our computation only on the edges of our domain. And the nice thing is that actually everything gets spread out over all possible threads. So that is a rather nice approach. Okay. And then of course, yes, you can use single and a single task for the first section. That's indeed also possible. So in that respect, sections, to be honest, is something I hardly ever use, since in a way it's more elegant to do that with single and then a task. That is, in a way, nicer programming. Okay. Then this is the same thing, but again in Fortran. Don't think there are any surprises here. All right. Then, talking a little bit about OpenMP 5. So basically that's more recent, 2018. Major differences. So now we have a reduction clause on task loops that was already mentioned, and there's also task loop SIMD. So basically that means that you can also ensure that the tasks that are generated by a task loop are in fact vectorized. So that's rather interesting. So collapse typically only worked for loops that were independent, in the sense that the index of the inner loop should not depend on the other loop. That was originally not allowed. And now with OpenMP 5, you can actually do that. You can collapse loops where the starting index, for instance, or the boundary depends on the index of the outer loop. So that is possible. And the default loop scheduling is changed from monotonic to non-monotonic. Of course, if the schedule is not static and without the ordered clause. So basically, that can also help a bit with implementation and optimization under the hood. So that's not really something for the programmer, but it's something that is useful to know. Okay, and then dynamic and guided, blah, 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 we know. And yeah, the end of the day, you want to try and minimize overhead. So that was why that was introduced. Okay. Then a scan option for reductions, which basically means that you are accumulating things like a scan, a parallel scan. Task reductions, yeah, okay. And smaller things, okay. But we don't get any details here, unfortunately. Okay, pity. Okay, some conclusions. I would say that OpenMP 4, OpenMP 4.5 and OpenMP 5 actually address quite some interesting new things. They're listed here. We have just discussed them, so maybe let's not go there again. Okay, let's, by way of example, do this exercise, the PyTask loop. But I'd first like to talk a little bit about, I'd first like to ask whether there are any questions. Let's start with that. That's probably smarter. Okay, no questions. So let's maybe just give you a glimpse on what it looks like to program GPUs with OpenMP. So this is not the scope of this course, but I want to mention it anyway, since it is actually a very good motivation for using OpenMP. If you're familiar with GPUs, you know, of course, that the market is dominated by NVIDIA at this point in time, but that AMD is making inroads. Now, of course, if you think of GPU programming, then most likely you're thinking of CUDA, which is, of course, NVIDIA specific. And everyone else is going to tell you that they have tools that automatically convert the CUDA code to whatever their proprietary programming thing is. AMD is going to tell you it has Hipify, which basically means a translator from CUDA to HIP. HIP is their version of something CUDA-like. And of course, Intel is going to tell you the same thing. They also have GPUs for computing nowadays, and they will also happily tell you that you have a converter that will magically turn your CUDA code into whatever they use for dealing with their GPUs. I don't have one, so I can't tell. I even don't have access to one. So in that respect, I don't know too much about it, in all honesty. And of course, that works to a certain extent, but it still means that your main code base is in fact tied to a single vendor. And okay, you can say, well, okay, I have an AMD, so I'm going to develop in HIP and then whatever. But yeah, it has always annoyed me when doing GPU programming that I had to really buy into a single GPU vendor in a sense. And that's one of the nice things about OpenMP, that you can actually consider doing GPU programming with OpenMP. There has been for quite a while another programming library available, which is OpenACC, and that looks suspiciously like OpenMP. So that's been available for a while. It was developed originally by a company independent of NVIDIA, but NVIDIA bought that company. So yeah, there's still a link to NVIDIA. So the advantage of OpenMP is that, yeah, basically you can write code that will run on NVIDIA hardware, but also on AMD hardware. And that is, in my opinion, a rather nice feature. So we can quickly have a look at how that would pan out in practice. So let me just start a new tab here. And switch directories. Oh, what is happening here? Ah, okay, yeah, that's because the shell was a leftover of yesterday and I run it the first time, so blah, blah, blah. Doesn't matter. Okay, so let's go to GPU programming, source code, OpenMP. So basically, you can do several things. Most examples here are C and C++. It works for Fortran, but I didn't do any examples yet. So this is work in progress. So it's intended to be a separate training about using OpenMP to program GPUs. But as you can see, it's very much work in progress. I'm definitely not there yet. But we can have a look at how you interact with devices. So basically, that's rather simple. You can get OMP, get num devices. So that gives you the number of GPU devices that are detected by this application. So of course, this is very straightforward. So basically, here this is a bit more involved. If I'm on the initial device, basically that means if I'm on the CPU, then I print I'm running on host. However, as you can see, this is a Pragma OMP target. So essentially, I would like to run this on the GPU. But of course, if there is no GPU, then this will still happily run, but it's going to run on my CPU. Okay, so in that case, I'm just printing that it's running on the host. And otherwise, I'm going to check how many teams I've got. So basically, that's more or less the number of things I can sort of do in parallel. And then I can check the number of threads for each team, which goes here. So as you can see, now it's running on the device with teams and threads in each team. So these are things you can inquire about. And I really have to look at this code because it's very badly formatted. But apart from that, it's just to show that indeed, and if this runs on a CPU, on a GPU, you will indeed get the appropriate output. Okay, this is all not so very interesting. So let's have a look at, for instance, something that at least does a computation. So let's look at vector product GPU. Okay. So we have a few vectors, actually arrays of floating point values. I'm going to allocate those. So this is a simple malloc. So this is host memory. Vector A, vector B, and vector C all living on in the host memory. Just checking whether they're actually all initialized. Malloc didn't return a null pointer. If that's the case, of course, I have to bail out. Otherwise, I can continue. I'm doing all my computations in single precision, basically because I'm very often developing on my own system that has a gaming GPU rather than a compute GPU, and the gaming GPU doesn't do double precision. So that's why everything here is single precision, why I'm using float, and also why I'm very explicit here that this is a float value in single precision. That's what the F actually means, in case you would not be aware of that. Okay, so I'm going to initialize my vectors, blah, 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 some initialization. Now things get more interesting. I have a target construct, target directive here. So basically, the for loop is intended to go onto the device. So I'm going to have teams, and I'm going to loop. But of course, my data needs to get to the device. And that's accomplished using the map clause. Remember map? I mentioned it at some point with respect to vector slicing. And that's indeed exactly what we're going to do. So basically, I want vector A to go to the device. I want vector B to go to the device. Which range? Well, everything from the beginning up to nx. And remember, nx is the size of my vectors. So basically, this means start at the beginning of the vector and go for nx elements. So that would mean vector a0, vector a1, etc., up to vector a nx minus 1. Okay. So I put a and b, vector a and b on the device, but there is only the to clause here. And then I have another map construct, map clause, which says to from. So basically that means before you start this block of code, please transfer vector C to the device. And when you're done, please transfer the result back to host memory for vector C. That's not going to happen for vector A and vector B. Since I'm not going to change them in the loop, I only want to put them on the device. I don't want to get them back. I only want the result get the result back, because that's the only thing that actually changes. And this I can accomplish with a map from to from. Of course, you can also have just a map from, and that basically means that the data was originally allocated on the device itself. So if I allocate an empty array or a non-initialized array on the device, I use that in some computation by filling it with values, then I only, of course, need a from clause in order to get that to the host memory. Okay, so this is basically, these are my data clauses. They ensure that the data between host and device gets mapped and also gets transferred. Okay, so this is a loop construct. So basically these iterations over my arrays are going to happen on the GPU. Map directive is like, yeah, it's sort of mem copy indeed. Yeah, absolutely. But it's sort of more done automatically in a way. Because with CUDA, you would have to do an additional mem copy and also synchronization step. Well, you mem copy your data in, you synchronize, you invoke your kernel, you synchronize, and you get your mem copy of the result. So it would be a bit more explicit. Here, a lot of implicit stuff happens. The two happens before the kernel starts, if you want to call it, because this is going to be my kernel in a sense. So before the kernel starts, I'm going to ensure that the data is transferred and also that things are synchronized. So my kernel is not going to start before the data transfer is complete, and vice versa. Before it's safe to transfer vector C back, it's not going to happen. So there is an implicit synchronization there as well. Okay, the rest of the code is not particularly interesting. So of course, this is a pretty trivial example in the sense that, yeah, typically your data resides longer on the GPU than this. So essentially, there are two ways to get data onto the GPU, which is called structured and unstructured. So essentially, that means you have a data transfer directive that will move your data to the GPU, and then you can do whatever on the GPU with that data, and then you end that with a sort of end directive, and your data is transferred back to the GPU. But meanwhile, you can launch 1, 2, 3, whatever many kernels you want that actually use that data. So that is quite convenient as well. Unfortunately, I didn't manage to do the Julia OMP, GPU version yet. So that is something that I should still do. So as you can see, the material is in a very early stage, but more to be added later. So this is just intended to give you a flavor of what this would look like. The big advantage, again, is that this code is happily going to run even if I don't have a GPU. So normally this should work nicely even then. Let's see, for instance, if I would compile this with GCC, and I'm not going to use OpenMP now, then normally this guy should actually compile. Yeah, okay. What's the... to power. Okay, I have to add the lm. As you can see, it compiles happily. Okay. No, this is not a vector. Is this not a vector product? Let me see. I don't remember. Might be. Yeah. Okay. Yeah. It's an element-wise vector product, essentially. That's the... no, a vector product? No, it's not a vector product, actually, because I have C already... yeah, no, why is it not a vector product? No, it's a vector. Yeah, it's a element-wise vector product. So is that what you mean? So basically, that I should also add over the vector C, all the elements of the vector C, and then you have a dot product. That's what you mean. Yeah, okay. Or do you mean something else? Wait, what's happening? I'm doing. Yeah, okay. No, this. Yeah, no, you're actually quite right, because this for loop here actually has nothing to do with my vector product. Yeah. Okay. So why is it there? I mean, why did I actually put the second for loop here, which is, well, just ensuring that I really a lot of computations, basically to see the difference, to see whether there's a benefit of doing that on a GPU, and there will only be a benefit when the computational load is large enough. So this inner for loop is in fact just here, add a lot of load to my computation. So to make it worthwhile to put on a GPU, because of course I have to offset the time of data transfer. So if I would really do just a simple vector product, it's very unlikely that I would see much performance benefit. So that's basically why that inner loop is there. So yeah, it's not really well named in that respect. I will definitely agree on. Also notice the size of the data, which is here. It's a pretty large number. So that would be, I think, 2 gigabytes. Well, 2 million, no, that can't be 2 million elements. That would be a bit much. How much is this? So that's 1,000, okay, 200 million elements, essentially. Yeah, 200 million elements. So that would amount to in 800,000 bytes. So this is approximately, say, I don't know, 2.5 gigabytes of data or something. So to transfer that takes a while. And that's why, of course, it only makes sense to do that in the first place when you've got some work to do in your kernel. Otherwise, it doesn't weigh up. And since this is a stupid example, in the sense that I just have a single iteration over my loop, yeah, that really would never ever be worth the data transfer. So that's why I add a lot of load using the loop over J. Yeah, true. Okay, so that was basically what I wanted to show you here. What you can do, if you like, is ask more questions, that's for sure. What you can also do, if you like, is have a look at, let me quit this, let me go to project source OpenMP. And what you can have a look at if you want is the heat map example. So heat conduction. Yeah, I know it's a directory. So, oh, Alice. So basically, there is the serial code and also vectorized code. So if you like, you can use that as a starting point and then try to do the parallelization. You find the whole thing on GitHub. And I'll put the repository in the chat. Here it is. And basically, there is a lot of other stuff here as well. So let me go into the source code for a second. So in the OpenMP directory, you find a few things which can be interesting. Some things are just experiments. Well, most things are just experiments, essentially. So here, for instance, in iterators, there should be some C++ code normally. There should be some C++ code which shows how to do a parallel for loop over a C++ vector, because that has a random access iterator. So I can actually happily do that. Okay, I should really not do the master thing here. That's stupid. I should do single, but okay. In this case, it doesn't matter that much. Anyway, as you can see, I've got a vector iterator, and here it's very explicit, but I can happily do an OMP4, put some schedule there, do a reduction, etc., etc. Here would be the same thing, but explicitly iterating over the with explicit indexing. But apart from that, it does the same thing. So that allows you to time things if you're interested. Other things that might be of interest. There is an experiment whether if you have the Fortran block statement of whether that will do the right thing or not. It would with gfortran. It would last time I tried, not with ifort, but okay, you can't have it all. It's not in the specification, so you can't expect it to work. There are some other examples like level parallelism as well. Something about re-entrant functions, which I mentioned, that your function should be thread safe when you call them from different threads in your parallel team. There are some examples of tasks as well. Normally there should be, if memory serves, yeah, Fibonacci tasks. Well, I thought I had also a quick sort in parallel, but that doesn't seem to be here. That's a bit bizarre. Let me see. No, I don't have that. I really thought I had. Weird. I remember doing that at some point, but okay, that code disappeared somewhere without me realizing where it is. This one could also be of interest. So this nucleotides thing, that is basically doing I/O from multiple threads, and the idea essentially is to, if memory serves, get some DNA data and then count the number of A, C's, G, and T's. So there's also some Python code to actually create data normally. And apparently I've done some benchmarking stuff here as well. So if you like, you can have a look at that. As usual, the thing is available. Let me maybe switch to main. Oh, okay. I shouldn't do that. Get status. Let's look. There is some. Okay. So don't trust the count nucleotides thing too much, because apparently I have been still fiddling with that. But the C code seems to be stable. Okay, so I have to, I can't switch now without stashing and so on, which I don't want to do. I also don't want to commit this since I don't know what the changes are. Okay, so let's just have a look at the GitHub repository instead, because that is the main code. Well, that's the master anyway. So yeah, most of the things seem to be in the main thread already. Okay, yeah, so there's nothing too much in development that seems not to be in the master thread. Well, in the, not the master thread, the main branch. Okay. All right, so what do you want to do? We have 10 minutes left. So if there are any more questions, please feel free to ask. If you want to do the heat map example, for instance, that might be a very good idea. Apart from that, for some reason, I've also done this in single precision. Not sure why. Okay, no problem. Hope you enjoyed it. So this is the heart of the code. And of course, as you can see, it's a nested do loop. And we compute the temperature at point ij with a very simple kernel, basically the temperature at the neighboring points and the point itself, but in the previous time step. That's essentially what's happening here. We compute the difference between the two time steps, and then, of course, we are interested in the largest difference. And that is what the while loop controls, or what that controls a while loop. Okay. Why is that already? Oh, that's interesting. So I thought, okay, let's look at the serial version. It was actually the plan. Not to look immediately at the code. Of course, the main computational load of this is this this do loop here. And here I do something different. Why? There is no while loop here, so I'm doing a fixed number of time steps for some reason. Don't know why. Okay, it doesn't matter. Anyway, so basically, this is a time-consuming step. So essentially, you would have a choice to either just parallelize the outer do loop, to parallelize both do loops, or to put a collapse on them, or to parallelize the inner do loop. You have quite a lot of choices here. So it might be worth to experiment a little bit and to see what gives you the best performance. You may think about it a little bit and say, well, okay, my guess is that this will be best, and then test your hypothesis and see what's best to parallelize. Then you might also want to think what you want to do. Where do you want to open your parallel region? Would you do it inside of that do loop, or would you take it outside of that do loop? And then the question is, what are you going to do with these things here? So that's also something to think about. Then you might remember, oh, there is such a thing as first touch. and I'm actually initializing my TMP data, my temperature data here in this nested for loop. And besides first touch, I also want to make sure that actually if I have the data in the caches at this stage, that my threads here for this do loop end up on the same course where the data is already in cache. So how would I do that? So these are all things you might want to consider. So you can parallelize that pretty trivially by just adding a parallel do here. And then you can start refining by, for instance, ensuring that the parallel is not called in every loop of T, but outside of it. Then you might want to experiment what happens if you also do the initialization in that same parallel region. If you ensure that those guys here actually get the same iterations, there's already a problem, because J is iterated over from 1 to n. Here it's iterated from 2 to n minus 1. That's annoying. So there are quite some things which you might consider when you're actually parallelizing this thing. What also could notice is that I'm using pointers here in order to swap the temperature and the previous temperature around. In Fortran, that might not be your best bet. So again, there are things to consider here. And also, it's very easy to switch this from single precision to double precision and back. The only thing you need to do is to change what FP is an alias for. So if I want to run the whole thing in double precision, I only have to change the 32 into 64. And then the whole thing is double precision rather than single precision. Okay. Question? Then the L3 cache. Yeah, so of course, if everything fits in L3, then of course it depends. If you're running on a single socket, because L3 is part of the chip of a socket, then of course if you run on a single socket, all your threads run on that socket, it doesn't make any difference. But as soon as you are attempting to run more threads than fit on a socket, so you're using 2 sockets on a 2-socket system, and then of course it starts making a difference, because then if you don't initialize using the same parallel scheme as you do in your processing, then the first touch principle comes into effect, and all the threads on your second socket are going to have to get to the data using hypertransport. And that will incur some load imbalance between, on the one hand, the members of the team that reside on the first socket, and on the other hand, the members of the team that reside on the second socket. So that has less to do with whether it fits in L3 or not, but more with how many threads you want to use, and whether you want to spread those threads over multiple sockets or not. Yeah. Okay, so compilation. So if you have a compiler like NVCC or NVC++, if you're using the HPC toolkit, compilation is always going to be done on the host. So the host is going to generate the code. It's also going to generate a code that will run on the GPU. So the kernels are indeed in a library that contains instructions that are going to be executed on the GPU. So that part of the code cannot run on the CPU. It's a different instruction set between obviously your CPU and your GPU, but those instructions are being generated on the host. So I can happily compile and build an application on a node or on a computer that doesn't have a GPU. I won't be able to run it. That's a different story. But building, yes, because I don't need, as such, the GPU in order to compile and build my code. So that is possible. I can compile on a system that is not that has no GPU. Of course, it should have all the GPU libraries installed, because otherwise you can't link. That's pretty clear. But I never tried, but I'm pretty sure that if you don't have the drivers installed, that you can still happily build your GPU application, your CPU, your GPU applications. Of course, you can't run them with NVCC and NVC++. They are not going to allow you to run them if they're CUDA. Does that answer your question? Okay. All right. Then another question, in case I ask for X cores on the HPC while on the same socket, if X is this code. Unfortunately, you don't know. Well, it depends. So it depends on which HPC system you're talking about, because configuration of clusters is not uniform. So, for instance, on tier 2 systems, it's often the case that jobs of multiple users can run on a single node. And then, of course, you just get assigned a bunch of cores that may or may not be on the same socket. You don't know, because that will depend on what another user is doing. So that's one answer. If you're running on tier 1, then you don't have this problem, because at least it's single user, but I think, if memory serves, it's even single job. So I don't think that 2 jobs can end up on the same node on the current tier 1 system, VSC tier 1 system. But you would really have to check the documentation of what can happen there. However, if memory serves, and if you're using Slurm, then you can actually put some extra information there. Let's try and find that, but that will not be easy because I don't need to tell you that there is like a billion options to as badge, and finding the right one, which I want now, that is going to be interesting. Yeah, that's going to be very nice. Okay, this is just number of cores. But here I can set cores per socket, so this gets more interesting. So of course, if I set the number of cores per socket to something that fits on a socket, which I of course have to, but if the total number of cores doesn't exceed that, then this is actually going to happen. So this would already solve your problem. This would help you to ensure that your job will only run when all the threads can be allocated to cores on a single socket. So this would already help you. And probably there are also ways to do placement with Slurm as well. But again, I'd have to look a bit further because I know that they're there, but I'm not even sure that they're always supported. So I think that's also something in the configuration, whether that's actually supported or not. But the CPUs per core per socket is already going to help you. Yeah. Okay. So that would indeed help you. Yeah, that would solve the problem for now. Okay. Any further questions? If not, let's conclude because I also still have another meeting to go to, so I'd have to close up anyway. Okay, for those of you who are also attending MPI next week, if you have any OpenMP questions, we can discuss then as well. And otherwise, you can always email me if you have more questions, then I can see what I can do to help you. All right, I wish you a pleasant remainder of the day and certainly a pleasant weekend. And I'll see you hopefully in some other training or some other occasion wherever in HPC land. So, all right, see you around and thanks for attending.